Hello guys, welcome to our third and last video on the single machine total tardiness problem. In the previous video we finished to establish the benchmark of the simple heuristic first comes first served, which is at the end of the day scheduling the activities in the order of the letters of the alphabet. Not a great heuristic, but okay, we know that this heuristic for this problem will give us 259 days of total penalty. So now we're going to proceed to create the mathematical programming model and ask a solver, commercial solver, to solve it. Okay, so before we proceed, please note that all the code related to this video is going to be down in the description below. So let's start. We're continuing with the same notebook on the previous video, and let's go ahead and create our model. And that's something really easy. We have to store the model inside the variable, and we're always going to start with an empty model, and then this empty model is going to be populated first with the variables, then objective function, constraint, and finally once the model is completely full and we are sure that the model has everything that we need, we're going to proceed to solve the model using a solver. So to create an empty model, we start with this function from Pyomo, concrete model. We open parentheses and we just leave it as it is. That's a model that is completely empty. Okay, so we run it, no errors, perfect, we have our model. So let's start creating our variables. We're going to say that these variables are going to be inside M. Inside our model M, we're going to create the variables that we're going to call jobs. And this is going to be, actually let's start with a set of indexes that we are later going to be used to create the variables. That's going to make our life way easier. So we're going to call pyomo.set, and we are going to initialize this set. So we provide the argument initialize, and it's going to be equal to initialize, and it's going to be equal to, well, to the keys of my data. Okay, that means data.keys is going to provide all the index values from A up to J. So good, we have this, and let's also create another set that we're going to call pairs, and this is going to store all the combinations that we created in the pairs variable. Okay, all that's going to be useful when we create the binary variables. Okay, so we're going to again initialize, and this is going to be equal to the prod, those variables that we created here for the combinations. Well, we're going to store them here. Okay, good. So we have these sets. Let's run them. They are created, but these are sets that we're going to use for creating the variables. Okay, so let's start with the variables first. So we're going to call m.x. Those are our x variables. Actually, let's make them uppercase. Are going to be equal to what? To pyo.var for variable. And we're going, how many variables do we need? Well, that's easy because we created this set, so we just need to pass that. Hey, we need x variables equal to the number of values inside the set jobs, and we need to establish the domain. Okay, the domain, that means the range of values that these variables can have, and we're going to say that okay, all the values here for the start date, they have to be non-negative. And let's start with reals, because the way we are formulating this problem, if we, instead of using integers, we use reals, it's gonna work out at the end, and it's gonna make way easier for the solver to solve the problem. Okay, so we're gonna create this. That's good. Now let's proceed to create the due date values. So we're going to call m.p, uppercase p, and this is going to be equal to pyo.var, and again I'm going to have a past due variable for each one of my jobs. Okay, and this is also going to belong to the same domain. Okay, good. And then finally let's create our y binary variables. So this is also going to be pyo.var. Now here is not m.jobs, now it's m.pairs, so it's all variables inside this set. And the domain is not going to be the non-negative reals, it's actually going to be binary variables. So pyo.binary. Okay, So these are our variables. Perfect. So the variables are created, and let's proceed to create the objective function. Okay, so now let's proceed to create the objective function, and as we know in the objective function what we want to add is all these p variables. Okay, so that's pretty easy. Let's create inside our model M an objective, and we're going to, now this is not going to be a variable, it's going to be pyo.objective. So we let the autocomplete work for us, and objective requires an expression, expr, and what is going to be this expression? Okay, we're going to add, but we're going to add what? Well, we're going to add all p values dot j, okay, for all the jobs inside m.jobs. Okay, so that's going to create my expression for the objective function. Okay, and we also need to provide the sense for this optimization. Okay, so in sense we are going to tell this objective if we're trying to minimize or maximize. So here in this case we set up pyo.minimize, and that's it. That's our objective function created. Okay, so this is our expression, and sorry, I forgot to put the in mjobs for the for loop, that's why I was giving an error, but now if we run it we will see no errors. Perfect, our objective function was created. So now let's proceed for the constraints. Okay, so let's create the constraints. So for the first constraint, let's create a constraint list that we're going to call m.c, and this is a list that it's going to contain all of the constraints that we described inside the presentation. So it's po.constraint list. Okay, so we leave it open, and then we are going to loop, because the constraints here, at least for this one, it's going to be initially equal to, for all the jobs in the set mjobs. Let's start adding the first constraint. So we're going to call m.c.add to add a constraint. Okay, so our constraint, well, that's going to be an easy one. Is the one that says that the finish of a job has to be less than or equal to the due date plus the deadline of the job. Okay, so that's pretty easy to do. So we are going to call m.x.j, that's the start date of the activity, plus the duration, and that's inside data.j dot duration. Okay, so that's the duration of that given activity, and that has to be less than or equal to the due date of that activity. So we know that that's sorry, this is not activity, that's j, because that's the variable that we're using for the loop. This is equal to due plus what? Well, plus m.p.j. Okay, so that's my constraint. That's the only constraint that I need to add here. Well, that's the first constraint that we need to add. Then we're gonna need to add the constraint about the pairs, but this one, it's the first one that we need to add. So we're going to run this. No errors, great. So now let's proceed to create the pairs constraint, the one that is going to enforce the model to schedule each activity or each job in our model separately. We cannot schedule jobs in parallel. Okay, so for that we're going to need a number, a big N number. In this case, for this problem, if we add all of the durations in our data in our dictionary, we're going to notice that this number is equal to 99. So let's go ahead and initialize m to 100. And let's go ahead and create the for loop that is going to allow us to create the OR constraint. So for all the pair of jobs j and k that are in m.pairs, in the set m.pairs, okay. So for all of those, we need to add two constraints. If you remember the presentation, we need to add two constraints, m.c.add, and what we're going to add is the start of activity j plus the duration of activity j has to be less than or equal to the start of activity k plus our big M number multiplying the y binary variable, so the m dot y, and this is a binary variable that has double index, so j dot k. Okay, so this is the first constraint that we need to add here of the pair, and then n dot c dot add the older version of the constraint. So it's the same part here. It's just that we need to change the index to k, and this has to be less than or equal to what? To the start of activity j now, plus big M multiplying 1 minus our binary variable, and this one is the same, j comma k. Alright, so these are our two constraints. So if we run this, no errors, great. So now let's check this model, and we can do this using a very handy function from Pyomo. Each model that you create, you can call ppprint with parentheses because it's a function, and if you run this, you're gonna see all the information that you put in your model. As you can see, the set of jobs, it's all of the activities from A to J. Then here the set pairs contains all of the pairs, okay? Here we are declaring the variables, so we have the p variables, the x variables, and then the binary variables y. And here we have the objective function, which is exactly what we wanted, the sum of all of the due dates of the penalty dates. And here we have our constraints, okay? All of our constraints. Good. Perfect. Okay, so now that we have the model completely created, is the moment to solve. So first of all, we need to establish a solver, and we're going to store the solver inside a variable that we're going to call opt. We're going to call from Pyomo the function solver factory, and here we're going to ask with an index, with a string, what is the solver that we want to call. So in this case, let's call Gurobi. Okay, it's the fastest of the solver that we can call here in Pyomo. Okay, so we're going to create this, and then finally we're going to ask this opt variable that contains the solver to solve our model. Okay, and we're going to store the results inside a variable that we're going to call results. So here we're going to call opt. We're going to ask for the method called .solve, and here we're going to pass first the model, that it's our model m, and we're going to provide this extra argument. We're going to set it equal to true because we want to have all of the verbose associated with the solution. Okay, that's to monitor how the model is progressing. So since I'm interested in knowing how much time this is going to take, I'm going to use a magic method of the Jupyter Notebooks .time, double percentage symbol .time. Okay, in any case, this is also going to provide the same information, but let's call this and let's run it. Okay, as we can see, it was initialized. This is all of the verbose of Gurobi, and that's it. It's already finished. Okay, so it took Gurobi 36.5 milliseconds to find a solution. Okay, good. Let's see. This is the entire optimization model, and it reached optimality. Okay, optimal solution. We can see here that it says optimal solution found. That's exactly what we want to look for, and we know that the optimal solution was found, and with an objective function of equal to 152. Remember, our starting of the model was equal to 259. Now we are at 152. Okay, so now we have this. Let's go ahead and extract the solution. So if we use this function from Pyomo.value, and we call it from for a variable, for example, for obj, we're going to see that Pyomo.value will give us all of the numeric values that are inside these variables. Okay, so this is good because we can use this to establish to extract the solution. So we're going to make a loop. So for all j in my m jobs, that's going to allow me to loop through the variables. Okay, and let's store all of this information inside a variable that we're going to call schedule. It's going to be a dictionary. Okay, good. So now we're looping. So what we want to do, well, for that variable j, okay, we're going to create a dictionary in which we're going to have an inner key that we're going to call job, and this is going to be a little bit redundant, but it doesn't matter. We're going to store the job j there. Then we're going to have the start, and the start is going to be equal to what? Well, we're going to round this because remember we were using real numbers, so it's going to be equal to m.x.j. Okay, and we are going to pass here that the round is equal to 0. So that's our start date. Or finish date is going to be equal to this, same as above, plus data.j.duration. Okay, that's the finish date. The due date of that activity, that's also going to come from our data dictionary. And the amount of penalty days, the delay, that's stored in another variable. That's going to be equal to what? To sorry, this has to be inside pyo.value. If no, we're not going to get the corresponding numeric value. pyo.value, yes. Yes. Alright. Yes, close here, and this parenthesis is not going here. Okay, perfect. And this is gonna be pyo.value of what? Of m.p. that's containing the number of penalty days, the due date, and we're gonna also want to round this to 0. Okay, perfect. So if we run this, we should produce our schedule. Let's explore what we produce, what we were able to extract. And this is the schedule. Okay, so we're starting job A on day 30, we're finishing on day 39, and this is the amount of the delay that each activity has, and that's the optimal solution. Okay, so if we want to now extract what is the sequence in which we want to schedule these activities, now that we have the schedule, if we want to know exactly the sequence that will allow us to get the optimal solution, so this is very simple. Let's create a new variable that we're going to call A, and let's transform all of our list of job keys into a NumPy array, because this is going to allow us to generate this sequence pretty easily. Okay, for x in my schedule. Okay, so we're going to create another variable called order. We're gonna use so we are going to create a NumPy array, because this is going to allow us to call the argument sort method. So we're going to try to order to create a list of all of the start dates of each one of the activities. Okay, so for x in schedule. Okay, so we're going to create this list, and now we're going to transform it into a NumPy array, and now that is transforming the NumPy array, we're going to call the method argument sort. Okay, so this is going to order all of this NumPy array from the smallest to the biggest one of the start dates, but is, instead of returning just the minimum and maximum value of the start dates, is going to return the index of where these values are sorted. Okay, so if we transform this into a list, we can directly use it to sort A, and that's what we're going to use. So now that we have the order, we're going to call our NumPy array that now is storing the index of the jobs, and we're going to transform this into a list. Okay, so we are going to run all of this, and let's call what is inside A, and this is giving me the optimal solution, CFBI HIAEJDG, and this should give me 152 days of penalty. So now that we have this order, if we go back into the game and we try this, we should see the optimal solution and we should win that game. So let's go here and let's input that solution. So it says first C, then F, then B, then auto I, then H, then A, then E, then J, then D, and then G. And indeed it's 152, and if we look at the results, now we don't have to pay any penalty. In fact, we're able to make a profit and we won this game. So this is how we solve these complex combinatorial and optimization problems using Python and Pyomo. I hope that you have liked this video series, and please let me know if you are interested in these videos down in the comments below. Thank you, and I'll see you again in another series. Bye.